Hi everyone, my name is Navi Suresh and my teammate is Kosalia Badmanathan. We are here today to discuss a topic that impacts every Malaysia road we travel, slope stability and foundation. Okay, the contents are Bukit London slope failure analysis, and the second one, foundation selection for commercial buildings and soft ground. The third one is presentation about the structure and slide development guide about the case study 1 and case study 2. Okay, let's start with the case study. The site condition, a 12-meter high soil slope with 38-degree inclination with the constructed during highway maintenance. Post construction issues emerged after heavy rainfall, including cracking and toe seepage is highly plastic clay with electric material. Observed problem surface crack appear at the slope crease indicating tension failure development. Water seepage at toe suggests saturated condition and potential piping failure mechanism and soil properties. Highly plastic clay exhibit poor drainage characteristic. Lateritic materials may contribute to strength loss when the saturated and subject to weathering the process. Okay, I will begin by setting the context of slope and foundation issues are critical challenges in Malaysia civil engineering. Climate environment. Our frequent heavy rainfall is a primary trigger. It significantly increases the pore water pressure in the soil, which lead to slope failures, particularly in common materials like clay and lateritic soils. Um, then slope stability concerns. The issues are particularly prevalent the hillside and highway project, such as the well-known events at Bukit Lanjan or Highland Towers. The combination of poor drainage and step slopes drastically worsens the instability. Then the third point is about the engineering importance. The highlights why careful geotechnical investigation and design are essential for ensuring the long-term safety and durability for the infrastructure. Okay, to understand the current case study, we need to classify the failure, the material properties here, such as a rotational failure type. Rotational failure, this is a typical for clay soils. The failure surface develops as a curricular slip, driven by the soil's cohesive properties and shear strength. The second one is the progressive failure. We should be aware that the failures start small and the crack at the crest, like those in our case, such as a tension failure that erupts backward from the final slip surface. The third one is total stress analysis. Since our case involves a highly plastic clay experienced rainfall, undrained condition, the analysis must consider total stress, including the crucial effects of poor pressure development. To meet the required FOS of 1.25, we have three primary stabilization options. First is drainage improvement system. This is often the first step as it directly targets the cause of high pore water pressure surface and the subsurface drains control seepage, which can improve the FOS by 15 to 30 percentage just through effective water control. The second is soil nailing system. This provides active reinforcement that nails the internal friction resistance along the failure surface. This method offers substantial improvement, typically raising the FOS by 1.2 to 1.8 times. The third one is retaining wall support. This provide passive and external restraint force at the critical toe area. It mechanically reduces the driving moment at, and increases the resisting moment. The capable of an FOS improvement ranging from 1.3 to 2.0 times. Okay, now we proceed with the felonious method for a stability analysis, which is suitable given the assumed circular slip surface, the highly cohesive clay. For a step one, slip surface, we first assume a circular surface and then divide the sliding mesh with the vertical slices. Step two, forces the calculation. The core calculation determining the weight of each slice and resolving the force into normal and tangential and then components along the failure surface to establish equilibrium. Step 3, factor of safety FOS. Finally, the factor of safety is calculated. The Felonius equation determines the FOS taking the sum of the resisting moments provided by the shear strength and dividing it by the sum of the driving moments caused by the weight of the soil, all calculated around the circle center. The analysis result based on the given parameters, the 38-degree and slope and 12-meter height, the calculated FOS is only 0.89. Analysis result says the required FOS is 1.25. A calculated FOS of 0.89 means the slope is currently unstable. The driving moment is exists and resisting moment by the 12 percentage and the critical slip surface passes through the vulnerable toe region. This requires immediate stabilization and measure for the safety complements. The remedial measurements. Our analysis shows that a simple slope angle reduction to 30% significantly increases the FOS. Additionally, implementing drainage installation can reduce pore pressure, providing a 25 to 40 percentage improvement, and nailing can add a sustainable zero point 0.3 to zero point 0.5 FOS merchant.
Hello, my name is Kosalya Padmanathan. Today I am presenting about case 32. The topic is foundation. Here is some information about foundation. First of all, site conditions. Two-story commercial building planned on site with 8 meters of soft clay overlaying dense sand layer. Original design proposed pet footies but engineer recommends deep pile foundation system instead. Structural requirements: two-story commercial building generated significant debt and life loads requiring adequate bearing capacity and minimal settlement characteristic. The lastly, soil profile: 8-meter thick soft clay layer with poor bearing capacity overlies, competent dense and stratum with excellent load bearing characteristics. Next is foundation selection analysis and recommendations. First of all, shallow foundation limitations. Soft clay provide indicate bearing capacity for commercial loads effectively. Excessive settlement potential exceeds allowable limits for structural integrity. Long-term consolidation creates differential settlement and building distress issues. Next one is deep foundation advantages. Load transfer bypasses weak soil and reach competent bearing station below. Minimal settlement through and bearing and friction resistance combination machines. superior long-term performance and structural stability for commercial building requirements. Next is Taragi's bearing capacity analysis for soft clay. Here F bearing capacity theory. Taragi's bearing capacity equation for clay soils under undrained conditions. For soft clay with Cu 40 kilonewton per meter square and footing with 2 meter, the ultimate bearing capacity is significantly limited by cohesion. Theory, Theoretical bearing capacity analysis confirms shallow foundation intensity for commercial building loads on soft clay. Here graph for bearing capacity comparison. The yellow one is shallow foundation and the blue one is deep foundation. The next one is foundation design, parameters and analysis summary. Comprehensive comparison of shallow versus deep foundation performance characteristics for the commercial building project, showing technical and economic consideration for final design selection. The parameter is first one is bearing capacity. The recommendation is deep rigor. Design impact is critical. Second one is settlement. Design impact is excessive. The recommendation is deep preferred. Third one is construction cost. The design impact is moderate, and the recommendation is acceptable. Fourth one is long-term performance. The design impact is critical. Recommendation deep reward. Lastly, construction. The design impact is moderate, and the recommendation is manageable. Next one is engineering recommendation and the best practices. First one is design implementation strategy. Both case studies demonstrate the critical importance of comprehensive geotechnical investigation and appropriate engineering solution selection based on site-specific soil condition and structural requirements for optimum performance. Second one is top stability management. Implement comprehensive drainage system for pore pressure control measures, regular monitoring of slope deformation and groundwater condition continuously, establish emergency response protocol for rapid remedial action implementation. Third one is foundation design optimization. Conduct through soil investigation to determine bearing stratum depth accurately. Consider long-term settlement and consolidation effects in design calculation. Evaluate construction methodology and equipment access for deep foundation installation. Next is safety complaints. Maintain factor of safety above 1.25 minimum requirements. Next is performance monitoring. Establish instrumentation for long-term structural health assessment programs. Lastly, economic optimization. Balance initial construction costs with long-term maintenance requirements. That's all for now. Thank you for your attention. From me, Kosalya Batmanathan and Navitira Surash.